So what we're going to try to do is learn some real, like an introduction to proofs, but an introduction to proofs using things that you all know very well. So has anyone had a course in geometry? Okay, great. You've all had a course in geometry. So this is going to be a course in geometry done formally. And you'll see what I mean by that. But before we do that, let's go back to like, what is math actually about? What is, I'm gonna take notes for you, and you can also take notes as well. What is mathematics at its core? What do you guys think? Sam, you got something for us?
Manipulation.
Okay, so so one suggestion is manipulation of numbers and variables. What else? Who else got something for us? Yeah, Viva.
Extending logic to its limits.
Extending logic to its limits. Okay, I like that. Extending logic to its limits. And we might add, and sometimes beyond its limits. Maybe we'll see some of that. What else? Yeah, Jimmy?
An abstract representation of the real world.
An abstract representation of the real world. I like that. So there are lots of different ways that we can do mathematics. For me, I would say at its core is the search for universal truth. So the search and discovery, invention, if you like, we're not going to get into that argument now. The search or discovery of universal absolute truths. Things that were true to Euclid 2,000 years ago are still true today. And that's not the same, you know, physics as it was understood by Newton is not physics as was understood by Einstein, is not physics that was understood by modern practitioners of the art and science. So that's one of the main differences between other subjects and us. The problem, if this is your sort of golden shining star, your North Star, the direction we want to head in is truth, is how do you know who's right? So let me go back to, let me just show you kind of the difference between, let's do a little bit of history lesson, small mini history lesson. So has anyone heard of this thing, YBC 7289? Anybody heard of this? So there's a little tablet, YBC 7289 is what it's called. This is the Yale Babylonian collection, has thousands. You good? The Yale Babylonian collection has thousands, tens of thousands of these little pieces of clay. And they like fit in the palm of your hand. And you used to take a little reed and stick the reed into the clay in different ways, and you could make little shapes. Let me see if I can zoom in on this. So there's like this shape and that shape, and those shapes, you know, eventually people figured out those shapes had meaning. And the meaning on that, let's see, can I copy this? Let's try something. Copy image and paste. Wow, cool. Okay, so that's the shape. And what's the meaning? Go here. The meaning, let's see, they probably have it here. Here we are. Here's the meaning. Copy image and paste. Beautiful. So right here, you see this? That's a 1. This is like a vertical line. These are little carrots. So different parts of the reed, you would poke it with the top of the reed, you poke it with the bottom of the reed. And with the top of the reed, you make a 1. And with the sides, that makes a 2 and 1, 2, 3, 4. So this is a 24. They're writing in base 60. And then this is a 5 and a 1. That's 51. And that's a 10. Can anyone think of what this might possibly be? So if you know that they're writing in base 60, so here's a hint. So question, mystery. Here's the mystery. You find this thing in the ground. You date it. So you find this little ball of clay, this ball of clay in the ground, by various means, it was dated to the year 1800 around, roughly, I'll say, dated to, just to be crude, 2000 BC. Now, think about 2000 BC. How long ago are the ancient Greeks?
1,000.
2000 years ago. You go back 2000 years, you get to the year zero, right? Because Jesus. You go 2000 years before that, and you get to these people, the ancient Babylonians. So they predate, it's like we look back at the Greeks and say, wow, that was a long time ago. The Greeks look back at the Babylonians and say, wow, that was a long time ago, by the same amount. Okay, so this is a really long time ago. You go back and date it to 2000 BC. You find this ball of clay, and what the heck is it? And the mystery is, what is it? What does it mean? Well, if you knew something about the Babylonians, they used not base 10, but base 60. They used, so Babylonians, Mesopotamians, they used different systems throughout time and different circumstances, but one of their most robust things is base 60. They also use base 12 in some places. By the way, anybody have the time? How many hours are there in a day? 24 broken into two things of 12. So 12 is how we keep clocks. And how many minutes are there in an hour? 60? Where do you think that comes from? Okay, so this all traces back to these kinds of ideas. So given that they do things in base 60, let's find out what 1 plus, if this is meant to be 24/60ths, and then this 51, maybe this is 51 3,600ths, 60th squared. And then maybe this 10 is, what do we think? Yeah, 60 cubed, whatever. Okay, what is that number? So this number is approximately, I don't know what. Let's find out. So can I just search for it? It's approximately this number, 1.4 whatever. It's approximately that. There's somebody in here who I know likes lots of digits of square roots. Tommy, I always see your square root of 3s and square root of 5s. Does this look like anything?
Square root 2.
This is square root of 2. This is square root of 2 to very many decimal places, or sexagesimal in the case of base 60, decimal places. Way more. So what is the square root of 2 itself? Square root of 2 itself is approximately, give me the square root of 2. That. Oops, I didn't get the 1. 1.414213 instead of 212. So this is accuracy. This accuracy is within what? 1 part in tens, hundreds, thousands, 10,000s, 100,000s, a million? Millions? Is that where we're up to? And 1 part in a million accuracy. This is way more than necessary for any engineering or economic, people were trading, they would have a number, no one has a million sheep to trade. This is way more accuracy for any engineering or economic application. So this is where I would say it's the difference between this to me distinguishes this document, this object, this clay tablet, distinguishes this object from as being mathematics as opposed to engineering, as being mathematics as opposed to engineering. It has no practical application at the time. There's no reason you would want that much accuracy. You're just doing it because you can. Okay, has no practical application. that make sense? So already we're seeing the beginnings of real mathematics because you're doing things. We said mathematics is about abstracting away from the world. Okay, why root 2? What is this? Why is that the square root of 2? What does it have to do with the square root of 2? Well, what do you see?
Oh, it's the diagonal.
It's the diagonal of the square. If the square, this is a unit, then that's 1 and that's 1 and that's a right triangle. And so the Pythagorean theorem says that this squared plus that squared is equal to that squared, and this is 1 squared plus 1 squared is equal to, well, 1 plus 1 is 2, so this has to be a number that squares to 2, so it's the square root of 2. Does everybody see that? Does that make sense? So this number, y square root of 2, well, because, why is it doing this? Is it because I haven't zoomed in so much? I didn't think it, okay, whatever. Well, the picture shows the hypotenuse of a square. So if we use the side of the square as a unit, then the diagonal is square root of 2. Then by the Pythagorean theorem, the diagonal is square root of 2. Oh, I see. It's because I'm doing double dollar signs. This one only takes a single dollar sign. Ha. That will look a lot nicer. And then there's an extra dollar sign there. And then there's an extra dollar sign there. Okay, I'm learning how to use, I'm playing around with the new toy in case you didn't notice. And it's a single dollar sign and then it'll look nice. No, please? Okay. Great. Does that make sense? So, by the way, when was Pythagoras? You know, roughly?
2,500 years ago.
Good guess. He's actually more like 500. Well, 2,500 years ago, correct. Not 2,500 BC, correct. 2000 Pythagoras, which is, by the way, this is around 500, 550, whatever, 500 BC. So they know the Pythagorean theorem 1,000 years before Pythagoras. Right? The Pythagorean theorem is something that was rediscovered in India and China and all kinds of places completely independently in Persia. Let me give you another example of such a thing. This is Plimpton 322, another object, another ancient object. This one's a little closer. Plimpton 322 lives in New York City. It's at Columbia. YBC is in New Haven. And it's a list. When you open this up, it's a tablet, again, like this big, with a very careful list of very large Pythagorean triplets, integer solutions to a squared plus b squared equals c squared. Okay, again, from a similar period. So let me copy this, paste it into here. What's that?
Wait, where does that originate?
This originates from Babylonian, Mesopotamia. So where did they find this one exactly? It's a Babylonian clay tablet, and it's got all kinds of triplets of the form a squared plus b squared equals c squared.
Yeah.
If you work out what this is. Let's not take the time to do that, but I just want you to be aware that there's lots and lots of such objects. This contains huge integer solutions to the Pythagorean equation, x squared plus y squared equals z squared. This again also from crudely 2000 BC. All right, so what's the difference between these objects, which are huge computations with no practical purpose, which I'm very happy to call mathematics. I would not call something where someone, measures a table and says, okay, this is how big we need to make it, and then you go and make it. That's not math. That's engineering. Nothing wrong with it. I mean, it uses math, but it's not mathematics. What distinguishes this version of mathematics from the things that we said, manipulation of numbers and variables. Yeah, well, engineering also does that. Extending logic to its limits. Okay, so whoever made these tablets was certainly extending logic past any practical reason, figuring out these numbers, square root of 2 to high accuracy, or finding these large Pythagorean triplets. Abstract representations of the real world. So you can imagine needing a square and needing to find the diagonal of that square and needing to find it somewhat accurately, at least. So that's an abstract representation of the real world. How about absolute truths? So it's true that the numbers they discovered were large Pythagorean triplets, and it's true that this number is a large approximation to the square root of 2, but it's missing one thing. Proof. What these are missing, all right? What these ancient objects are missing, what these ancient objects are missing to be, mathematics as we understand it now understand it, is proof. So there came a time when people no longer accepted fact as a truth. There came a time when people no longer accepted mere fact as the truth. They wanted a pair. They wanted a pair, which is first, what is the truth, together with how do you prove it? Together with evidence, proof, irrefutable proof. Let's see the earliest known to me, known today, proof is by a guy named Thales, is by ancient Greek named Thales. He's just before the Pythagoreans. The Pythagoreans were like exploded with proof. The reason Pythagoreans are famous is because they really made proof like the cornerstone of how they do everything. Here, let me tell you Thales's theorem. So Thales's theorem is the following. So this is Thales's theorem. You take a circle, draw its diameter, and put any other point on the circle. Okay, so of course words don't help us understand things, so let's see a picture of that. So let's draw a circle. Okay, let's draw its diameter. And let's put another point somewhere on the circle. Okay, and let's put a point over here. The diameter goes all the way across. Can we see this? Oop. There we go. You can see that? We got a circle, we got a diameter, we got some point. So let me copy this, just grab this whole thing. And let's paste it in. So there's our picture. You take a circle, draw its diameter, put any other point on the circle. And the question that Thales' theorem addresses, how does the angle from B to C to D, does this work? Angle BCD? Yes. Change. How does it depend? On C? On C. How does it change as C moves around? Okay, so let's make a little angle here. Angle from B to C. Oh, I got it the wrong way. From D to C to B. Oh, come on. Please, angle. Thank you. From D to C to B. There's that angle. Let me draw the line segments so that you can see them. From D to C and C to B. Okay, and don't show me. Yeah, okay. So there's that point C, and I want to know what happens to this angle as I get over to here, as I get over to there, maybe it gets smaller, maybe it gets larger. How does it vary with the point C? What do you guys think? Someone who doesn't already know the answer. 5 of you know the answer. How does it vary? Any guesses? Nadia? Should I show the angle? Here's the angle. And what does it measure here? There it's 90. But if I move it over here, it's going to become 90. And if I put it there, it's still 90. And if I put it there, it's 90. And there it's 90. And everywhere it's 90. So if we were Babylonians, we would say, check this out. The angle's always 90. That's a fact. Period. We're done. That's the story. Does that seem satisfying to you? So we check, and every time we measure it, the angle is 90 degrees. How do I do degrees? Degree? Wow, amazing. I'm having too much fun with this toy. So that's it. If we were Babylonians, just stating that fact might be enough, might be satisfactory. But you see how that's not satisfying. That's missing something. There's some very serious deficiency. But of course, today, all of you, I see the mental hand signals. Today, that seems deficient. Deficient for understanding. Understanding. Proof is a mechanism by which we get to true understanding. Okay? So what do you think? How can we prove this theorem? How can we actually prove this theorem? How can we demonstrate without a shadow of a doubt that that angle will always be 90, even if we don't measure? It was 90 before we measured. Sarah.
You can see that the two sides of the triangle are like changing proportionally so that you do sine, cosine, or tangent.
Okay, if we know about sine, cosine, or tangent, we can do all kinds of things. That's great. Yep. So we could use trigonometry. We could put this on a coordinate system. All of the stuff that you're reaching for because you have those tools. And it's great that you have those tools. That makes you a much more powerful mathematician than the people who addressed this question initially. But they didn't have those tools. And so we're going to try to prove it with both hands tied behind our back. We're not going to know Descartes. The reason we can relate this to x squared plus y squared equals 1 is because of Descartes in the 1600s. The reason you can go to trigonometry is there's some version of something like they understood similar triangles. Actually, not even yet. They didn't really understand similar triangles. We can talk about what they did or didn't know. Ian, you have an idea?
It's because that like side DB stays the same, so the corresponding angle always stays the same.
Well, that's a good guess, but if I move the side DB, if I move it wherever, the angle isn't going anywhere. So that's a good guess. I like that guess. Bye, Bob.
Going on line from center to the center.
Ah, very interesting. So this is the point in mathematics where something has to happen. Some kind of spark from outer space has to come and visit us and tell us, hey, here's an idea. Bye, Bob. Where'd you get that idea?
Similar triangle.
Okay, so you're seeing some pattern, you're seeing some reason to draw. So Vaibhab's idea is, here's an idea. And the currency of mathematics is ideas. We want proof, we want understanding, but really we want ideas. And by the way, it's not all ideas are good. All ideas are valuable, even if they're not good. So you have to throw out, the way I work is I have to throw out 20 ideas a day, and 19.999 of them will fit. And many days in a row, every idea I throw out fails. So we just have to try stuff. But Vaibhab's idea is try drawing a line or a line segment from the center A to this point C. Let's see what that buys us. Maybe that'll let us see something that we wouldn't see before. So now we've drawn this line. Let me record this little drawing. I don't want to see the angle because that's what we're trying to prove. I don't want to save that. Just let's record what happened after we drew that line. Okay, here's the situation. Now what?
I thought of joining the center of DC with the diameter center.
Oh,
Yeah.
you're saying the center of DC, the midpoint of DC, and the diameter center?
I thought of that.
Okay, sorry, I misunderstood what you were suggesting. There is something that some mileage that we can get out of this construction. Yeah,
We know
so-
that all interior angles, at 180 or.
we, let's say that we do. Suppose that we do know that.
So then.
So Soham wants to bring another idea into the mix. Whoops. Where am I? No, there. Another idea. Suppose that we know that the sum of interior angles in a triangle add up to 180 degrees. Then what?
So then we know that ADC and ACD are equal.
ADC, okay, so now that's another idea. So another idea, you're saying that angle ADC is equal to angle ACD? ACD. Why is that true?
Because I and the NAD are both radii, so they're symmetrical.
Yeah, AD and AC are both radii of the circle. So AD, you guys did this kind of thing in school, right? You all went through, none of this should be new. This should be a review, I hope. We're going to do it, as you'll see, we're going to do it really the proper way and at a sort of much higher level. Because AD and AC are both radii of the circle and hence equal. And hence equal. So what? So this, so what?
ADC, ACD are equal, and the same thing applies to ACD and ABC.
Right. Slow down just a little bit. So this triangle, ADC, is what kind of triangle? Yeah, so triangle ADC is isosceles. And you know that the base angles of an isosceles triangle are equal. Okay, so if these two sides are the same, then, well, there is a symmetry. There's exactly the symmetry that Vaibhav was proposing. I can draw it here. It's a little bit cheating to do it, but let's do it anyway. Give me the midpoint between this, and then give me this line segment. So now you see that there's this symmetry between these two sides, and that's why this angle is equal to that angle. Everybody with me so far? Okay, so the triangle ADC is isosceles, and hence base angles are equal. So that's what justifies the fact that ADC is equal to ACD. Let's give that a name. Let's call that angle I don't know, X degrees or something.
Yeah.
Okay. Then you were saying?
Same thing applies for ABC.
Same for ABC. ABC is also isosceles because AC and AB are radii. So this is also an isosceles triangle. So what does that mean? Let me pick on someone else. Other than Sandy. Troy.
Angle ACB is equal to angle ABC.
ACB is equal to ABC, great. So ACB, same for ABC, that is angle ACB is equal to angle ABC is equal to Y, say. Okay, for the same reason, we can repeat that argument. These AC and AB are radii, and so this is an isosceles triangle, so those are the same. And now what? Other than Vaibhav? Anybody see what to do? Ayan, can I pick on you? Can you give Ayan some support? So this angle is X, this angle is also X, this angle is Y, that angle is also Y. So what? If we add all of them up, we'll get the angles in triangle in triangle DBC. This is X, that's X, this is Y, that's Y. If we add this plus this plus this plus this, that's the sum of all the three angles in the triangle. Everybody good? Jimmy.
That would be 2x plus 2y is equal to 80 from X, Y is equal to 90.
Okay, so you're exactly right. Let me take it a little bit slower than that. Everybody follow that? But angle D, I'll just say at D, the angle at D plus the angle at B plus the two parts of the angle at C. So that's DCA plus ACB. So this is angle DCA plus angle ACB, and I'll put parentheses around these because those two add up to angle C. That's equal to 180 degrees. And those are, exactly as Jivan said, that's equal to X plus angle D was X, angle B was Y, and then the two angles X plus Y plus X plus Y, which one's which? DCA is also X, and this one is Y. Everybody see that? Angle D plus angle B plus the two angles that make up angle C add up to 180 degrees. D is what we call X, B is what we call Y. These two are again X and again Y. So this is 2 times X plus Y. Therefore, angle C, which is X plus Y, is equal to 90 degrees. Okay. Phew. That was quadrate demonstratum, QED. We solved it. We proved it. We demonstrated it without any shadow of a doubt. Does everyone follow this proof? Does everyone understand what we did? There's one thing that's still not entirely settling about this. So we've realized why the angle at C, like without the lines, it's not even clear that it's going to be 90 degrees. We proved that it is. Now we really deeply understand why that's the case. But we had this idea to draw this extra line. Okay, certainly you can do that with straight edge and compass, right? You line it up, you draw it, no problem. And then we had some ideas. We know that the sum of the exterior angles adds up to 180. Why is that true? We know that if you have an isosceles triangle, base angles are equal. Well, we argued why that would be true, because if you drop it down the middle, then there's this symmetry. Every fact is justified in terms of another fact. Just like every word in the dictionary, in the English dictionary. How do you define vinculum? You define it in terms of other words. But how do you define those words? Also in terms of words. And those words are defined in terms of words. And what's the problem here? Other than Jim? Tell me.
Theorem.
Say
See an understanding of the words, you won't have to understand what it's trying to do.
So that's a really deep question. That's a really, really deep thing that you just said. Unless you understand the words, you won't understand the meaning of what you're saying. I would have agreed with that until just a couple of years ago, because now we have large language models. And those large language models, the reason they work is because words are defined in terms of other words, and then there's just a transition matrix from a bunch of tokens in context and then to the next token. And you believe that these models actually understand what they're saying, or they're just spitting out the next token, or maybe my brain is just spitting out the next token that comes out of my mouth based on the context of this conversation. That's a really, really deep question that you just asked. But it points to something very something else that's very deep, which is this idea of infinite recursion. If every fact, yeah, Vaibhav, you want to say something?
Might need like a fundamental level of truth that this is the truth, and from that you can.
Exactly, exactly. The problem is if every fact is proved using other facts, well, why are those facts true? Why are those facts true? And so on forever. There's an infinite recursion. You get an infinite recursion of facts based on other facts based on other facts, and you never actually get anywhere. If I start with a wrong fact, I can prove all kinds of crazy things. You know, if I start with contradiction, you get an infinite recursion of facts, and then how do you know? You're not proving nonsense? You're not proving nonsense. Let me give you an example. Here's an example of nonsense. Suppose that we've justified things back and back and back, and at some point we use the fact that 0 equals 1. Well, 0 equals 1 is a contradiction, right? Suppose our axioms, I said the key word, suppose the fact that we're trying to prove, suppose in proving a fact, we used another fact, namely that 0 is equal to 1. Well, that's a false fact. That's false, of course. That's a contradiction, right? That's a contradiction. So now let's prove the Riemann hypothesis. Doesn't matter what the Riemann hypothesis is. It's a $1 million problem. It's been around for 150 some odd years, 175 years. Let's prove the Riemann hypothesis. Okay, here's the proof. Assume it's not true. Assume the Riemann hypothesis is not true. We have this fact 0 equals 1. 0 equals 1 gives a contradiction. Therefore, the Riemann hypothesis is true. QED. $1 million, please. Okay, so what's wrong with this? Yeah, you can't assume a falsity of something and then think you're going to get someone. So how do we know that in our infinite recursion, we're not going to, at some point, rely, theorem A is going to use theorems B and C, and theorem C is going to use theorems D, E, and F, and theorem F is going to use theorem G, and theorem G is going to use the fact that 0 equals 1 to prove theorem G. Like this, it's what's it called? A house of cards. The whole thing comes tumbling down. There's no foundation. There's nothing to stand on. Does that make sense? Why this is not a good way to do things? Our whole house of cards can come tumbling down if it turns out that we used things that look like, well, if we use facts that depend on other facts that themselves depend on other facts. And you guys see, is it too low if it's down there? Rodrigo, you can see? Okay, let me slide it up. That depend on other facts that depend on something like 0 equals 1. How do we know that we're not just hiding the somewhere else we've proven a false statement? How do we tell that we haven't hidden, I guess, we haven't hidden a false statement in this infinite recursion? Okay, so what's the answer? What's the key word that makes this possible, other than Jiven? Jeremiah, you got an idea? What do you do to stop this infinite recursion?
You have to start with something that's known as truth.
You have to start with something that we hold these truths to be self-evident. It was just the 4th of July. You guys read the Declaration of Independence on the 4th of July? No, that's not me. That's the look I'm gonna get. You should read I'm an immigrant to this country. You should read the Declaration of Independence every 4th of July. It's an amazing document. We hold these truths to be self-evident. No document like this that's not true. There are lots of Venezuela has a constitution and that looks just like America's, and the country runs very, very differently, shall we say. Okay, so we hold, so Jeremiah, say again what you said. What we have to do,
We have to start with something that we know as true.
yeah, again, know that we declare, we hold these truths to be self-evident, that we declare to be true, or at least that we say these are the foundations of our theory. Okay, we have to start with something that we declare to be true. Those are called the axioms. Okay, so what the Greeks stumbled upon, which is still the way mathematics is done today, is that you actually need three things. It's not enough to have just the fact, the truth. It's not enough to have just the proof, the reason why that truth is there. It's a third thing, which is what foundations are you starting with on which you're going to prove the things that you establish as truth. Okay, so we actually need a triplet. First, axioms on which to build a theory. Then the next piece is the fact that you want to prove the theorem that you want to prove from those axioms, and finally the proof. Okay, so this is how all of mathematics from that realization on has been done. So far, so good? Okay, and what document is the epitome of this in the case of, I was about to give it away, geometry? Other than Vaibhav, other than Jivan? Anybody know?
Wait, can you repeat the question?
The question is, what document is the ancient epitome of this ideal? Tries to realize this in sort of the cleanest, most comprehensive way. You guys learned, you all took geometry. And you, is that a hint, Rodrigo? No. Henry? You know what it's called?
Is it like Euclid's like element?
Euclid's elements, bingo. Euclid's elements. That's exactly right. It's Euclid's elements. So let's look at Euclid's elements. Let's have a glance. Here's Euclid's elements. I'll put a link to it in the notes. I'll post all these notes. I'll show you once I figure out how to post them. I'll show you where I'm going to post them. What's that?
I never learned this.
You never learned Euclid's elements. That's okay, but you did geometry.
Yeah.
They just didn't call it Euclid's elements. The source of all of our understanding of this book until the 20th century. I don't know if this is still the case. Maybe Harry Potter beats out this book. But until the 20th century, there were two books that were the most published books of all time. Number 2 is Euclid's Elements. Number 1, the Bible. Okay, the only thing that beats Euclid's Elements is the Bible. The Euclid's Elements is the Bible of mathematics in a very real way. Okay, let's have a look. It's 13 books. We're not going to go through all 13, but let's look at book 1. What's in here? So book 1 starts with definitions. What are the objects we're dealing with? Then postulates, common notions, and then we go to the propositions. The propositions are his way of saying theorems. So what are the definitions? Definition 1, a point is that which has no part. Let's record that. Definition 1, a point is that which has no part. Okay, a point in space. Definition 2, a line is a breadthless length. By line, he means, you know what he means by line? Actually, he means a curve. Because he's going to say, and the reason I can say he means a curve, what we would call a curve, a breadthless length, that's because definition 4 is a straight line, is the line where the points lie, which lies evenly with the points on itself. Okay, the ends of curves are points, and a straight line, we'll skip a couple of definitions. Okay, then we talk about surfaces and plane surfaces and rectilinear and acute angles and obtuse angles and a circle. Let's get a circle. So a circle is a plane figure contained by one line such that all straight lines falling upon it from one point among those lying within the figure equal one another. That's a pretty awful way to say a circle, but there it is. That's a circle. There's a point called the center, diameter, yada, yada, equilateral triangle. Okay, this is interesting. I'll come back to that in a second. A square, what's a parallel? What does it mean for two lines to be parallel? When are lines parallel? When they keep the same distance from each other the whole time. No, we don't have a notion of keeping the same distance. What does it mean? Jeremiah?
When they're the same slope.
Okay, when they're the same slope, beautiful, except he doesn't have a notion of slope, Rodrigo. They never touch. Now, let's look at how he says it. Parallel straight lines, so first of all, he has to say straight lines, because lines for him mean curves. Parallel straight lines are those which, being in the same plane, I can have two lines that are not in the same plane, because he's also going to think about 3D geometry, and I wouldn't call these two parallel, but they don't touch. Okay, they have to be in the same plane, on the same piece of paper, so that if they are being produced indefinitely in both directions. So he's thinking of lines as segments of lines. So I want to extend both lines arbitrarily in both directions, forward and backward, do not meet one another in either direction. Okay, so these are two lines in the same plane that if you make them infinite lines, they never meet. That's what it means to be parallel. And now let's have a look at the postulates. So the postulates, we claim the following things are true. We claim that you can draw a straight line from any point to any point. Okay, so this is postulate 1. You can draw a straight line from any point to any other point. Of course, you give me 2 points, I'll draw the line through it. That's what this tool, where is it? That's what this tool does, right? Gives me a line or a line segment between any 2 points and I can just pull it. That makes sense. Straight edge, well, that's exactly what you're supposed to do with a straight edge. Postulate 2, to produce a finite straight line continuously in a straight line. So what that says, i.e., if you've drawn a segment, if you've drawn a finite segment, you can always extend it a little further if you want. Okay, if you give me a little piece, I can put that ruler right up to that little piece and draw it a little bit farther out. We're not thinking of infinite lines, although we really should be thinking about infinite lines, then you don't need this postulate 2. Postulate 3, to describe a circle with center and radius. What does that mean? What geometric object is he referring to when he says this? Physical object. What do you hold when you do geometry in high school? A ruler and protractor. Protractor I think of as measuring the angles, which is more like trigonometry. It's something that has a little bit more. It's a more modern instrument, an ancient instrument, Khalil. A compass. A compass only has 2 things. It's got a point that sticks in the paper and a little pencil that you swing around. Okay, so this means we have a compass. Postulate 1 is we have a ruler. There's 2 different things you can do with a ruler. You can take 2 points and draw a straight line, or you can, if you already have a line, you can just line it up to that line and extend it a little bit farther. That's postulates 1 and 2. Postulate 3 is you have a compass. That's exactly what a compass does. What's postulate 4? That all right angles are equal to one another. Why would he, what do you mean? 90 degrees is equal to 90 degrees. What are you talking about? Javen?
In terms of the size line.
Yeah, we have to go back to the definition of a right angle. What is a right angle? A right angle triangle. Where is it? Did I skip it? Where's the definition of a right angle? All right, I don't see it immediately. Ah, here we go. Here we go. It's definition 10. What you need to understand postulate 4 is you need to understand definition 10. When a straight line standing on another straight line, when 2 straight lines meet, so that the adjacent angles are equal to one another. If this angle is the same as this angle, that's when we call them right. So if they meet in a way that this angle really is the same as that angle, these are right. But here's 2 other lines, and they also meet. And these angles equal these angles. How do I know that something hasn't changed in how we measured it from here to here? That's postulate 4. It's that right angles are right regardless of which 2 lines happen to intersect. That's why he needs this postulate. And let's get to the last postulate. Anybody know what postulate? So again, postulate 1, you draw a straight line from any point to any point. Postulate 2, you draw a straight line continuously in a straight line. Postulate 3, you draw a circle with center and radius. But these are all completely obvious things, right? Postulate 4, all right angles are equal to each other. And postulate 5, if a straight line falls on 2 straight lines, making interior angles the same side less than 2 right angles, and 2 straight lines produce inevitably meet on the same side, which is with angles less than 2 right angles. Okay, everybody got it? This is the problem with postulate 5. If you heard of the famous parallel postulate, this is postulate 5. This is what all the fuss was about. And all the fuss was, so let's read this. Let's read this carefully. If you have, so I have to draw you a picture. And here's the picture. let's go, let's, and I have to let you go in 1 minute. So let's make sure that I do this. So if you have two straight lines and a third straight line, if you have, when a straight line falling on two straight lines make interior angles on the same side less than 2 right angles, this angle and this angle will add up to less than 2 right angles. Then the two straight lines, if produced indefinitely, if I continue extending this line and this line, they will meet on that side where the two angles add up to less than 2 right angles. So if this angle and this angle add up to less than 2 right angles, then if I zoom all the way out, come on, then if I zoom all the way out, eventually they will meet. That's the parallel postulate. That's this fifth postulate. That's a very strange, as you can see, that's a very strange thing to say is obvious. And we're going to talk next time about all the various things that people had to do. Let me give you one homework problem, which is to prove proposition 1, construct an equilateral triangle given a finite straight line. So your homework is prove this in, go to GeoGebra. In GeoGebra, and given a little straight line, segment, here's a little straight line segment, write down all the steps that you would need to do to draw. I'm going to use the polygon tool and just click from here to here. And, oh no, I want a regular polygon, sorry. I want a regular polygon tool from there to there, and I want a triangle. Yeah, that's cheating. There is no axiom that says I have a polygon tool where I can select a little segment and draw an equilateral triangle on it. So how do you do it for real? That's your homework. Okay, prove this proposition 1 that you can construct an equilateral triangle on a given finite straight line using those postulates. Okay,